Hello, everyone. Today, I'm going to present to you DiSH, a system for dynamically distributing shell scripts. This work was done in joint with my co-authors in UPenn, Purdue, and Brown. The project is open source, and you can find it on the link. So there are shells everywhere. And I don't mean these kind of shells. I mean shell scripts. The shell has been growing. And according to a study from GitHub in 2022, the shell is number 8 in the most used languages on GitHub. So let's take an example of a general data processing script. Say you have some data, and you want to do some things with it with a shell script. So you write some script, and then you get some output. So let's say you want to find the max temperature of some day. What you can do is you can go to a national agency and get some telemetry data for that day. So this is a piece of data for one day from a national agency. The numbers highlighted in red are the parts of this data where the temperature is mentioned. So if you want to find the max temperature in this script, you could write a script like this. This script reads the data using cat. Then it takes the characters 98 to 92, which are the ones highlighted in red. Then it removes any invalid temperatures, represented by 999. And then it reverses in reverse order and takes the first element. And that would be your max temperature. However, and this would take on your own computer like less than 1 second. However, data is growing. And this year, we're going to be storing more than double what we used to store in 2020. So let's say that now you want to take a data for a whole year. And for that, you decide to go and put your data on a distributed file system in your on-premise cluster. And for this example, we're going to use HDFS. So you have HDFS set up on your system, and you have your data in HDFS. The only thing you need to change to your script to make this work is change the first part, the cat, into the HDFS equivalent. And in this case, we maintain the same script, and this will give us the max temperature for a much larger data. And this works fine, right? Well, this ends up being really slow. For this script, for a 3.6 gigabytes of data, we end up spending 200 seconds on this script. And 95% of this time is spent only on the HDFS cat part, and that's because of the download speed. So you might decide to rewrite this whole thing in Spark, or you might decide to write it in Hadoop Streaming, and Hadoop MapReduce. But maybe you don't want to do that. Maybe you want to leave your own script as it is. And here comes DiSH. DiSH is a system that will turn your slow script into a turbocharged, super fast script. So if we look at the performance of the previous script, PaSh would take 200 seconds, as we mentioned. PaSh is a system for locally parallelizing your shell script. And that would take 190. And because we said 95% of the time is taken at download, so doing things locally to optimize wouldn't give you much. Hadoop Streaming, if you port that script into Hadoop Streaming, which is a system for like basically making mappers and reducers, you would get up to 90 seconds. However, DiSH would do it in 7 seconds. So what does DiSH do? DiSH takes your sequential script, and it transforms it into a data flow graph. Then it applies some more transformations on the data flow graph, and finally, it distributes it to a cluster of workers, usually co-located with your, say, HDFS cluster. And finally, DiSH does all of this without giving you a new shell. It works on top of your existing shell. So let's dive deeper. Say you have a script. And the first step that DiSH does is it uses its dynamic orchestrator. And the main job for the dynamic orchestrator is to handle the dynamic nature of the script. So let's look at this script. In this script, we have many variables that are expanded at runtime. So you have an ls. It has to look at your file system. It has to know, the files in your system. And then it has to expand all of these variables. And doing this ahead of time is impossible. What the dynamic orchestrator allows us to do is it invokes the compiler at every iteration of this for loop. And so it expands this at every iteration of the for loop, and then it invokes the compiler that eventually gives you very accurate distribution of the script. So after the dynamic orchestrator invokes the compiler takes your script and let's take this example of a very simple grep and then sort script. It transforms it into a data flow graph. So this data flow graph has an input, which is end.txt. Then there's a grep, then there's a sort, and then there's standard output. After that, the compiler applies our parallelizing transformations. So these transformations turn your data flow graph from sequential data flow into a parallel data flow. Finally, and this is formalized, and you can check it out in our ICFP paper. Finally, the scheduler takes what the compiler outputted, and it takes this data flow graph and distributes it into the workers. The workers, each of them have their own shells, and they can transform that data flow graph back into a shell script and then run it on its own machine. Finally, the output of these shells get back to the user shell, and you get your output. So let's see it for our example. So this is the script we started with. The first step, we turn it into a data flow graph. And it would look like this. We would have the input, which is temp.txt, then our cat, cut, grep, sort, and head. And finally, we would store it locally on max.txt. So this, we first apply what we call the DiSh file expansion. So we look at this file, and we see how many blocks is this file split into on our cluster of workers. And in this case, this file is stored as 2 blocks. The first block is on worker 1, and the second is on worker 2. So we now apply our parallelizing transformations, and you can see that by applying these transformations, we can execute everything up to the sort in parallel before having to do anything merging these results. So the scheduler now comes in, and it distributes this graph. So it realizes that the first section of this graph at the top can go to worker 1, which is where the data for block 1 is. And then the bottom half goes to worker 2, which is where the data is. And then finally, we get the final result at the host. And this leads to our very impressive speedups. Why is that? Well, in this case, we end up moving less than 100 megabytes on this link between worker 1 and worker 2. And finally, when we go back to the user, we're only downloading 1 line of data, which is the max temperature. And in this way, we eliminated 95% of the work that was consumed by the network. So, and if you're wondering if this is just for that script, you can see our results across many benchmarks. So on the y-axis, we have the speedups, and higher is better. And on the x-axis, we have a bunch of benchmarks. We ported many scripts into Hadoop Streaming, but for some scripts, we couldn't express them trivially with Hadoop Streaming, and we don't have results for those. And on average, Hadoop Streaming gives you 7.2 x speedup, while DiSh will give you 13.x speedup. And if you're wondering if this is accurate, well, it's not only fast, but it's also accurate. We test this with the POSIX test suite, and we only differ from PaSh in 2 test cases. And these test cases, we only differ in the error status of those. And you can see the other shells and how much they differ to PaSh. And the reason why we only differ in very few cases is because DiSh doesn't take your nice shell and turn it into a new shiny shell. What it does is it takes your shell and wraps it and orchestrates it without actually modifying its own behavior. It still uses your underlying PaSh shell in this example. So finally, what does DiSh offer? DiSh offers a system that can automatically distribute your shell scripts without requiring any developer effort, and it is fully compatible with your already existing shell scripts without any modifications. So thank you. You can check the project on GitHub, and this project will be merged into the PaSh project, which is part of the Linux Foundation. I'm now open for questions.